Hey, chemistry crew, Mr. Collier here. Today we're going to talk about Charles' Law, which is another one of the gas laws. This is page 9 in your gases notes packet if you're following along. So we're going to talk technically, but then I'm going to give you some examples that I think this is another one of those laws that makes some pretty intuitive sense. So Charles' Law is the relationship between temperature and volume. So I remember it as in Charles starts with the same letter as Celsius, which is what we measure temperature in. So that's kind of how I remember. But this law simply says that at a constant pressure, the volume of a fixed amount of gas is directly proportional to its absolute temperature. In other words, if you heat a gas, it expands, it takes up more volume, right? So here's your graph, volume and temperature. It's a direct relationship. As one goes up, the other goes up. We can write that mathematically like this: V1 over T1 equals V2 over T2. And if you just imagine putting numbers in here, just like sometimes we get deep into these equations with these fancy numbers, but like if you just think about just numbers for a second, like say you had 1 over 1, right? And then you wanted to make that bigger, but make that relationship still true. Well, 1 over 1 is 1. So say you made it bigger and the volume went up to 5. That means the temperature also needs to go up to 5 because 5 over 5 is still 1. So when you're doing these kind of mathematical relationships, sometimes it helps to just think about real simple numbers and put them in the equation and see what it tells you. You can also rearrange this equation by kind of cross multiplying, and you can get V1 T2 equals V2 T1, which is much more complicated to say, but it works exactly the same. So one more thing to consider here is that these temperatures must be in Kelvin. So you have to convert all of these temperatures to Kelvin or this equation does not work. So make sure you are using Kelvin. All right, a couple little diagrams and things like this. Here is a sort of visual. Say you had a container that was able to change its volume, right? Were you to heat this gas, they would run into the walls of that container more and they would expand, they would take up more space. So we keep the number of gas particles the same, we keep the pressure the same, and that's going to make the size of the container change. Another way to think about it is we've all had a balloon, right? And if you take a balloon from a regular temperature to a colder temperature, it's going to shrink. It's going to take up less volume. Gases will shrink when they get colder and they will expand when they get hotter. So if you ever buy party balloons in the store, go take them out to your car on a cold day, you're going to notice they shrink. You might think, oh no, I got a leaky one, but the reality is it's just cold outside and the gas is taking up less space. If you take those balloons back into your nice warm house, they're going to blow right back up to their normal size. One more little diagram, same general idea. Heat the gas and its volume expands, cool the gas and its volume contracts. We can do a bunch of different sample problems with these. Here is one. What is the Celsius temperature of 68.2 milliliters of methane if it occupies a volume of 0.02200 liters at 50 degrees Celsius? There's actually a lot going on in this problem. First of all, we've got two different units. We've got 68 milliliters here, but then you've got a volume of 0.022 liters, which 1, 2, 3, that would be 22 mils. So these two volumes aren't as different as they seem. But one thing to think, I always like to think big picture, is this 22 mils is less volume than 68 mils, right? So whatever has happened, we've made it expand to take up more space. So we must have heated it. So I'm expecting a Celsius temperature of greater than 50 in my answer. All right, so let's start setting this up. We want to use this relationship, V1 over T1 equals V2 over T2. And one of the things I've already gone ahead and done is to convert from liters to milliliters. I could have just as easily gone the other way. It would be okay to do both of these in liters instead of both of them in milliliters, as long as they're the same units. My volume units, again, one more time, doesn't matter what they are as long as they're the same. Temperatures, however, have to be in Kelvin. So I wrote 323. That number came from taking 50 degrees and adding 273 to it. That's where that number came from. Now to solve this, I'm simply going to cross multiply, right? That gives me 68 times 323, boom, equals T1 times 22. Divide both sides by 22, and we're going to get our answer in Kelvin, and it's 1001 Kelvin. So that is higher than 323 Kelvin. So the temperature did go up like I was kind of anticipating. But now let's just subtract 273 to get it back to Celsius. It's 728. So yes, indeed, we had to raise the temperature quite a bit to make the volume go up by as much as it did. So here's one more graph that kind of shows this. And this graph actually, I love this. It's a very important kind of graph, which is comparing temperature to volume. And as you trace it backwards, you'll notice that it's trending toward zero volume. That zero volume down here would hit the x-axis, the temperature axis, at negative 273. That absolute zero number that we've talked about a couple times, the coldest possible temperature, is not only when all molecular motion ceases, or all molecular motion ceases, but it also would be when the volume of a gas approaches zero. And you can't have a volume of a gas to be literally zero, although then there would be theoretically zero space in between each particle. And so that's why absolute zero is the coldest possible temperature. One last little law I want to sneak into these notes is Avogadro's law. It's a pretty straightforward one, and it's just about the N amount of a gas compared to the volume that it takes up. And this is actually what Avogadro was known for in his day. He didn't actually come up with Avogadro's number. It's sort of named after him, but Avogadro's law was actual science he did when he was alive. What he realized is that equal volumes of gases at the same temperature and pressure contain an equal number of particles. So the volume that a gas takes up is the same regardless of its molar mass, whether it's helium or radon. The size of the gas particle doesn't change how much fits into a certain amount of space. This is where that number 22.4 liters came from. He tested different gases and found that whether it was a big molecule or a small molecule, it always took up the same amount of space if he had the same amount of the actual gas. And that's because there's so much empty space between gas particles that the size of the particle itself doesn't really matter. And that comes back to this 1 mole of gas, 22.4, 6.02 times 10 to the 23rd particles at 273 K and 0 atmospheres. Here is that one more time. Again, because of Avogadro's law, if 3 gases have the same number of particles and they're at the same temperature and pressure, they're going to take up the same amount of volume. So if you fill up a helium balloon, an oxygen balloon, and a radon balloon to the same volume, they're going to have the same number of particles in it. Or if you release a known amount of particles, they're all going to blow up to be the same size. That should be everything you need to now go and do pages 10 and 11 in your packet. Practice with Charles' law, and I think a few simple questions about Avogadro's law. There's not really much math to do there. So that's it from me. Let me know if you have any questions. Good luck.